Okay. Let's see. I'm going to confirm it's recording here. Yes. Okay, great. So we have another type of equilibrium to discuss. This is called complex ion formation, okay? And it involves the formation of these so-called complex ions in solutions, just a different type of equilibrium. Generally speaking, they're going to oftentimes involve transition metals because they tend to be good Lewis acids. So it's kind of like a Lewis acid-base reaction. The base is going to donate an electron pair, and this Lewis acid, the transition metal, is basically going to accept that to form a new bond. This can occur, as this reaction shows, using water as our Lewis base. In this particular case, we've got our silver ion reacting with 2 copies of water to form this substance. So carefully at that for a second. First off, it's aqueous, it's dissolved in water. And we have an ion that's charged in which the metal ion coordinates with 2 copies of water. Now this ion will just float around the beaker like any other ion would. And this is called a complex ion. Complex ion is just kind of the generic term or name that we give for that type of compounds. Okay, so these ions that form by combining a cation with several different neutral molecules or anions, they're oftentimes anions, they're called complex ions, and this is one example of a complex ion. Now before we go on in terms of vocabulary, this word I guess is important. The ions or molecules which attach themselves to the metal cation are called ligands. So in this example, water is our ligand. It's just a vocabulary word, okay? If a ligand is added to the solution that will form a stronger bond than the current ligand, it will displace the current ligand. Example of that can be found here. If we take that silver complex ion, where water is our ligand, and we add some ammonia. Ammonia tends to actually be a pretty good ligand for this type of chemistry. So the ammonia will actually displace the water and replace it. We'll form this complex ion, and we'll regenerate our 2 copies of water. This is still a complex ion. It's an ion in solution, which a neutral molecule, a neutral ligand, is attached to the silver. It's just a different complex ion. Okay. Now, these complex ions oftentimes like to form an aqueous solution. So we'd like to develop a framework through which we can describe their formation in terms of equilibrium chemistry. And that's where we're headed with this. So the reaction between an ion and its ligands to form a complex ion is referred to as a complex ion formation reaction, or a formation reaction for short. So we're going to be talking about these formation reactions. Let's take a look at what their general framework looks like. For the one that we just considered, we have our silver plus 1 cation reacting with 2 copies of ammonia to make this complex ion. It's an ion, multiple neutral molecules attached, and through Lewis acid-base chemistry, it's a complex ion. That's what we make. We can treat this from an equilibrium perspective, and we can write the formation reaction and the associated equilibrium constant. We call these associated equilibrium constants formation constants, and we give them the symbol capital F, capital K, lowercase f, formation constants. It's nothing more than an equilibrium constant describing the formation of the complex ion. So how do we define it? Well, products over reactants, like usual. Our Kf for this particular reaction is the equilibrium molarity of our complex ion divided by the equilibrium molarity of silver plus 1 ion, our product, or reactant, times the equilibrium molarity of ammonia squared by virtue of the 2. It's just an equilibrium constant, products divided by reactants raised to their stoichiometric coefficients. Now this is one example of a complex ion, but in fact there are many different examples. This particular slide summarizes other options for formation of these complex ions. For instance, you could make a silver cyanide complex. Here's our silver ammonia. silver with fluoride even, hydroxide. Many different examples. And notice that a lot of transition metals are forming these complex ions in aqueous solutions. There's various different charges, there's various different ligands involved. You don't necessarily need to memorize this table or memorize all of the stoichiometric ratios or even all the ligands. But do know that lots of options exist. Usually the problem that you face will kind of point you in the right direction in terms of which complex ion you're talking about. But all these complex ions, they're different substances. They have different tendencies of form. Some of them have humongous Kf values, right? 10 to the 21st, 10 to the 35th. Other complex ions form less readily. 10 to the 3rd for this one is the Kf value, okay? Here's 1 times 10 to the 3rd. But in general, notice that Kf values are often quite large, aren't they? I mean, 10 to the 18th, 10 to the 33, 10 to the 19th, 10 to the 13th, even 10 to the 7th. What does that tell you about our reactions? If this reaction with the silver and the ammonia has a Kf value of 1.7 times 10 to the 7th, what does that tell you about that reaction? Doesn't it tell you it lies really, really, really far to the right? In other words, if you mix these two in solution, they are really good at sticking together to make this complex ion. Huge value of K. This equilibrium lies far to the right. And that's going to be important in a few seconds. So I wanted to point that out. K values tend to be quite large. Okay? So let's take an example or take a look at an example problem for this concept. Let's say that we're going to mix a 200 milliliter sample of a solution that contains copper with a 250 milliliter sample of a solution that's got some ammonia. We want to know after the solution reaches the equilibrium, what concentration of copper aqueous remains. This is copper 2 plus aqueous. This is the one that's unbound. It's not associated with the ligand. Okay, it's the free copper, you might say. I always like to start questions by drawing a picture, right? So I'm going to have myself a beaker. What goes into this beaker? Well, one thing that goes into the beaker is 200 milliliters of 1.5 times 10 to the minus 3 molar copper nitrate. And also into that beaker is 250 milliliters of 0.2 molar ammonia. We're going to mix them well, allow the things to reach equilibrium, figure out what happens, right? You with me on that? Alright, so let's think about a strategy here. I think the first thing that I would like to do to help solve this is figure out what the balanced chemical equation is, okay? So what help do we have or what guidance do we have for that? Well, it looks like we're mixing what? Copper with ammonia, right? Copper and ammonia. So let's look back to our sheet of complex ions and see if we can have any guidance with that. It looks like right there we find an entry for copper and ammonia. Copper coordinates with 4 copies of ammonia to make this complex ion. So why don't we start with that? Cu2 plus reacting with 4 copies of ammonia, setting up an equilibrium, formation reaction, in which we make CuNH3,4 in the aqueous phase, and that's going to be a 2 plus ion because the copper had a 2 plus charge, right? But we got to start with that reaction. So you can use this complex ion chart, I guess, to help you with that, with the stoichiometry, because it's not really always the same, right? I guess that would be the first step that I would encourage you to sort of master or do. Now, if I look up the value for Kf in that table, didn't make point of this at the time, but I'm Looking at it now, and the Kf value is 1.7 times 10 to the 13th. That's a pretty big K, so that reaction is going to move far to the right, and I'm confident in that already, okay? So how am I going to handle this to figure out how much of everything I've got, okay? Well, I think what I would like to encourage you to start to do would be to realize that because K is so big, these types of reactions tend to proceed to the right really quite far. So I usually like to make an initial assessment or estimate of where I'm at in these situations through use of an ICF table. And I actually oftentimes do that in terms of moles. I basically assume that this reaction goes to completion as far to the right as it can, and then I work backwards to reestablish the equilibrium, because you need to do that. So what I would do here is I'd figure out how many moles of copper 2 plus I've got by multiplying my molarity times my volume in liters. Now I was told the molarity of this solution is 0.0015 in the problem, and it looks like I'm using 200 milliliters, which is 0.2 liters. So pretty quickly, I can multiply 0.2 on my calculator times 0.0015 and come to the conclusion that I've got 0.0003 mole of this salt. And since I get 1 copy of copper per mole of the salt, that's how many moles of copper I've got, 0.0003. Now likewise, how many moles of ammonia? I use the same equation, molarity times volume in liters. I've got a quarter of a liter, 250 milliliters, a quarter of a liter, at 0.2 moles per liter. So if I do 0.2 times 0.25, I have 0.05 mole of ammonia. That's my initial inventory before the reaction of how much I've got. Now again, before the reaction, I don't have any of this because I haven't made any of it yet. But now I'm going to move to my C row, and I'm going to figure out how things change. This is where things pick up steam, right? So you look at your initial amounts and figure out essentially which one you're going to run out first, if you treat it as a limiting reagent problem, if you treat it as something that moves completely to the right for the time being. So I've got 50 millimoles of this, and only a third or so a millimole of this. I've got a lot more of this. So I'm thinking about this. If all of my copper was to react, all of it, how much of this would I need? Well, it looks like it's a 1 to 4 stoichiometry, isn't it? So if 0.003 mole reacted, I would need 4 times as much. I would need 0.0012 moles of this if all of this reacted. And if all of that reacted, I'd be out of it. But I wouldn't be out of my other one, would I? I'd still have 0.0488 moles of my ammonia left, because I could only consume this number of moles of it. Now in the process, I'd make some of this, and it looks like I make one of these for every 1 copper, so I think I'm going to make 0.003 moles of that, and because of that, at equilibrium, that's what I'm going to have, or at my final position. I shouldn't say equilibrium, but at my final position, that's how many moles of that I've got. Now, what I want you to realize is what I've just done here is a first approximation, because it assumed the reaction went to 100% completion. But what do we know about equilibrium? We know that the equilibrium constant for this reaction is large. It's 10 to the 13th, but it's not infinite, is it? So because of that, I need to come back and revise my first approximation, because it would actually predict 0 copper in solution. And we know that that can't be correct because it doesn't satisfy the equilibrium constant expression and this value of Kf. In other words, because Kf is not infinity, this first draft can't be completely correct, can it? So we're going to need to amend, make changes to that first draft. That's going to be our second half of this problem. So we write the reaction again. And this time, I'm going to treat it from an equilibrium perspective through a Rice table. This time, I'm going to enter in all my values in molarity units and not moles. So we have to make sense of this then. We got to convert these moles into molarities. Let's take a look how we might do that. Well, up above, I said that my initial first estimate was that all of this was bound up and I don't have any left. Okay, now I know that that can't be true, that I have to have a small concentration of copper, but for my Rice table I can start with the concentration at 0, I can make some, and then I'm going to have some small x amount of it. Okay? Likewise, for this one, I'm going to make some, specifically 4x. Because the equilibrium is going to have to shift back to the left here. But the thing is for this one, I don't have 0 starting concentration, do I? I used as much of this as I possibly could, and I still had this amount in solution. I still had 0.0488 moles. So I can't write a 0 molarity here. I need to write some non-zero number. Now, the problem is I don't know what that is right now, but I know have that many moles, and if I divided it by total liters, now I'd be in business. So what did I do to make this solution? Well, I mixed 200 milliliters with 250 milliliters. So my final volume should be about 450 milliliters. It turns out in reality, sometimes volumes are not additive, but for problems like this, we'll typically assume that they are, okay, unless we're told otherwise. So in this case, I think it's safe to assume 450 milliliters total volume. And if I do that, I take my number of moles and I divide by 0.45. 45 liters is 450 milliliters. I get a starting concentration of 0.1084 for my molarity of my ammonia. What about for this one? Well, in this problem, I figured out earlier that I made 0.0003 moles of it, and that's also dissolved up in 0.45 liters. So my starting concentration of this one is 0.000667. Now I'm going to use some of that. Now how did I know I was going to use some of it? Because in my initial amounts, I have some of this, but I don't have any of my copper, right? So this equilibrium could not possibly shift back to the right. And in fact, having a 0 here is a big problem because it doesn't satisfy my Kf expression. So I got to shift back left. So I'll use some of this in the process. I'll make 4x of this, and I'll make x of this. And at equilibrium, I'll have x, 0.1084 plus x, initial plus at 4x, right? And then for this one, I'll have my initial minus x. And that's going to be my expected amounts. So where do we go from here? Well, we just go back to our K expression like we normally would after working our Rice table. Kf is equal to my products molarity divided by reactants. This is a 1 for the stoichiometry. Now, the expected equilibrium concentration of copper is just x, so I put that in. My expected equilibrium concentration of this one is 0.1084 plus 4x. Now I also need to raise that to the 4th power, don't I? Right, because of that 4. And then when I look up my value of Kf in the table, my formation constant for this particular reaction, I get 1.7 times 10 to the 13th. And then that's what I write on my piece of paper for my KF expression. That's my equation. And if I could solve that for x, I would know everything that I need to make this work, wouldn't I? And that's what I'm going to do. Now, I'm looking at that value of k, and it's a huge number. So what I know is that, this stuff is really good at forming. This equilibrium lies really far to the right. I'm going to be pretty comfortable assuming that this x is really, really small. And that's going to help me out, because if that's the case, I can basically say that this is going to kind of simplify down to 0.000667. I'll ignore this x in the assumption. And then I'll make a similar step here in the denominator. At this 4x, I'll assume that 4x is really small compared to this 0.184. Still got to raise it to the fourth power, but that makes my life easier because it gets rid of that term and that term, right? I still got a little bit of work to do. It looks like I need to do the 0.1084 raised to the fourth power. Let me see if I can figure out how to do that on this calculator real fast. Seems like I got 0.000138 x, and that's now in my denominator. Raise this to the fourth power, and I got that number. I hope that that's right. And then in the numerator, 0.000667, and this still equals my KF, 1.7 times 10 to the 13th. So now I'm a lot closer. I just need to clear my denominator by multiplying it by both sides. So multiply by KF, 1.7 e to the 13. And I get 2.347 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9th. X has to be equal to 0.000667. So now all I need to do is solve for x. So 0.000667 divided by 2.347 e to the 9th. And lastly, I get x is equal to 2.84 times 10 to the minus 13th moles per liter. So boy, that's a pretty small number, but it's not zero, is it? It's not zero. So now what in the world does x tell us if we were to go back and look at our rice table? X tells us the concentration of copper 2+ in this solution. Indeed, x was very small compared to this number and that number, so our assumption is going to work out just fine. And we have now solved for the equilibrium concentration of copper 2+ in this reaction system as we were instructed. So it's just an equilibrium problem. Now, this particular example, notice that what I did at the start up here is I really worked it in 2 steps. My first approximation was my first step. I assumed that the reaction will go to completion as far as it possibly could first, right? And I just kind of worked it almost like it was a limiting reagent problem up here. Figured out which one I'd run out of first, and then I came up with these equilibrium or first approximation amounts, okay? And then I worked it from an equilibrium perspective because I said that the true concentration of copper could not be 0 because while the KF value is very big for this reaction, indicating it lies far to the right, 10 to the 13th is a huge KF, so we're really good at making this stuff, but it's not infinity. It's a large number, but it's not infinity. And for this to be 0, this would have to be an infinite K. We don't have that. So then we had to work backwards and estimate just how much copper we did have to satisfy the equilibrium concentrations required to make Kf value that number. So that was kind of our strategy here, okay? To pick up on that, it's useful to take that approach to assume limiting reagent first, and to explain why that is. We like to make simplifying assumptions when we can. If you tried to work this problem in one step from beginning to end, x would be a really big number, not a small number. And the reason why is because Kf is so big. But if you assume it goes all the way first and then work your way backwards, x becomes really small. And then the assumption is viable. That makes the math a little bit easier. And that's why I like to, for Kf or formation type equilibria, I usually like to work it in two steps like that, okay? So this is an example problem that shows formation of complex ions in solution. It's another type of equilibria. It's another type of equilibrium problems. Turns out this complex ion formation also can have effect on solubility. For instance, earlier in this chapter we learned that silver chloride is a sparingly soluble salt. It will dissolve, but just a little bit, not a lot, okay, to make our ions. But if you actually add some ammonia into that aqueous solution, this stuff is much more readily soluble. And the reason why is because the silver, once it's produced, can react with the ammonia to form this complex ion. This complex ion is not the same as this ion. They're two different substances. So if we make this, it basically sequesters away or stores the silver ion, pulls it out of solution, thereby solubilizing more silver chloride. And in fact, earlier this semester we learned to try to add equations together, and you saw that on your last exam, a sample problem on your last exam. But we learned that we could add equations together. If I add these two equations together, silver crosses out, and I get this. So I've got the silver chloride dissolving in aqueous solution in the presence of ammonia to make this complex ion in silver, and this complex ion in chloride. Well, remember, if you add the equations together, the rule is that you have to what? Multiply the K values, the equilibrium constants for each individual reaction. And if I do that here, the equilibrium constant for this reaction when the ammonia is present is only 3 times 10 to the minus 3. That's like 1,000,000 times bigger than this one, over 1,000,000 times bigger than this one. So if no ammonia is present, the silver chloride is not very soluble. But boy, if you add some of the ammonia and give it access to this reaction, you can really improve the molar solubility of this sparingly soluble salt. And this analysis basically kind of proves that, okay? All right, so the major ideas here, if I'm going to summarize for you to study for this particular section, one thing that I want you to be able to do is write formation reactions. Got to be able to write the formation reactions. I think that's super important. 2, I think we should be able to work. Well, how about, before I get to there, okay, write formation reactions. I want you to be able to write Kf expressions. That's the equilibrium constant, right? Products over reactants. That shouldn't be too difficult, I don't think, if you could do the first one. And then I needed to be able to work the equilibrium problems to predict the equilibrium concentrations of the metal ion and the complex ion. And then 4, it'd also be kind of nice to know that complex ion formation can affect solubility, as I just spoke of. Okay, so, and how that might work, okay? So, as I'm looking back through my notes here, it seems to me that that covers most of the bases for this particular section. be able to write those KF expressions, be able to write the actual chemical equations, and know that this occurs through Lewis acid-based chemistry. If you're able to do those things, I think you're probably good to go.